in module 5, the last bit is control systems components. To implement process control, the computer must collect data from and transmit signals to production processes. Process variables and parameters were classified as either continuous or discrete, with the several subcategories existing in the discrete class. The digital computer operates on digital data, whereas at least some of the data from the process are continuous. Accommodations for this difference must be made in the computer process interface. There are different components, namely sensors for measuring continuous and discrete process variables, actuators that drives continuous and discrete process parameters. Third one, devices that convert continuous analog signals to digital signal. Fourth one, devices that converts digital into the analog signals. And the fifth one is input and output devices for the discrete data. Now, the first one, that is sensors. A wide variety of measuring devices is available for controlling data from the manufacturing process for use in feedback control. In general, a measuring device is composed of two components, a sensor and a transducer. The sensor detects the physical variable of interest, for example, temperature, force, or pressure. The transducer converts the physical variable into alternative form, qualifying the variable in the conversion. The quantified signal can be interpreted as the value of measured variable. In some cases, the sensors and transducers are the same devices. For example, a limit switch that converts the mechanical moment of a lever to close an electrical contact. To use any measuring device, a calibration procedure is required to establish the relationship between the physical variables to be measured and the converted output signals. To ease with which the calibration procedures can be accomplished is one criteria by which a measuring device can be evaluated. A list of desirable features of the measuring devices for the process control are presented in the below table. Few measuring devices achieve perfect scores in all these criteria, and the control systems engineers must decide which features are the most important in selecting among the variety of available sensors and transducers for a given application. Consistent with our classification of process variables, measuring devices can be classified into two basic categories: analog and discrete. An analog measuring device produces a continuous analog signal such as electrical voltage. Examples are thermocouples, strain gauges, and potentiometers. The output signal from an analog measuring device must be converted to digital data by an analog to digital converter. A discrete measuring device produces an output that can have only certain values. Discrete sensor devices are often divided into two categories, binary and digital. A binary measuring device produces an on and off signals. The most common device operates by closing an electrical contact from a normally open position. Limit switches operate in this manner. Other binary sensors include piezoelectric sensors and proximity switches. A digital measuring device produces a signal output signal either in the form of a set of parallel status bits or a series of pulses that can be counted. Now, the next one is actuators. In industrial control systems, an actuator is a hardware device that converts a controller command into a change in a physical parameter. The change in the physical parameter is usually mechanical, such as position or velocity change. An actuator is a transducer because it changes one type of physical quantity, say electrical current, into another type of physical quantity, say rotational speed of an electrical motor. The controller command signals is usually low level, and so an actuator may also include an amplifier to strengthen the signal sufficiently to drive the actuator. A list of commonly used actuators is presented in the table. Depending on the type of amplifier used, the most actuators can be classified into electrical, hydraulic, and pneumatic actuators. Electrical actuators are the most common type. They include AC or DC motors of various kinds, stepper motors, and solenoids. Electrical actuators include both linear devices and rotational devices. Hydraulic actuators use hydraulic fluid to amplify the controller command signals. The available devices provide both linear and rotational motion. Hydraulic actuators are often specified when large forces are required. Pneumatic actuators are compressed airs will be compressing the air as the driving power. Again, both linear and rotational pneumatic actuators are available because of the relatively low air pressure involved. These actuators are usually limited to low force applications compared with the hydraulic actuators. Now, analog to digital conversion. Continuous analog signals from the process must be converted into digital values to be used by the computers, and digital data generated by the computer must be converted into the analog signals to be used by analog actuators. Now, sensors and transducers. This is the measuring device that generates the analog signal. Signal conditioning. The continuous analog signal from the transducer may require conditioning to render it into more suitable form. Common signal conditioning steps include filtering to remove random noise and conversion from signal form to another, one signal form to another. For example, converting current into the voltage. Multiplexers. The multiplexer is a switching device connected in series with each input channel from the process. It is used to timeshare the analog to digital converter, that is ADC, among the input channel. The alternative is to have a separate ADC for each input channel, which would be costly for a large application with many input channels, since the process variables need only be sampled periodically. Using multiplexer provides a cost-effective or alternative is dedicated ADCs for each channel. Now, the amplifiers. These amplifiers are used to scale the incoming signals up or down to be compatible with the range of the analog to digital converter. Analog to digital converter, it is the name, as the name indicates, the function of the analog to digital indicator is to convert the incoming analog signal into the digital signals. Now, digital to analog conversion, process by which digital signals are converted into the analog signals. For example, a modem converts computer digital data into analog frequency signals. that can be transmitted over the telephone lines. Now, input or output devices for discrete data. Discrete data can be produced by a signal computer without needing the kind of conversion procedures required for continuous analog signals. As indicated earlier, discrete data is divided into three categories: binary, discrete data, other than the binary, and pulse data. The first two categories, that is binary data and discrete data, are communicated between the process and computer by means of contact input and the contact output interfaces, while the pulse data are entered into and sent from the computer using pulse counters and pulse generators. Now, what is contact input or output interfaces? Now, contact interfaces are the two types of input and output. These interfaces read binary data from the process into the computer and send binary signals from the computer into the process, respectively. The terms input and output refer to the computers. A contact input interface is a device by which binary data are read into the computer from some external sources. It consists of a series of samples, contacts that must be either closed or opened. Now, the next one is pulse counters and generators. Discrete data can also exist in the form of series of pulses. Such data is generated by digital transducers, such as optical encoders. Pulse data are also used to control certain devices, such as stepper motor. Pulse counter is a device used to convert a series of pulses into digital values. The value is then entered into the computer through its input channel. The most common type of pulse counter is one that converts electrical pulses. It is constructed using sequential logic gates called flip-flops, which are electronic devices that possess memory capability and hence can be used to store the result of the counting procedure. Pulse counters can be used for both counting and measurement applications. A typical counting applications might be to add up the number of packages moving past a photoelectric sensor along the conveyor. A typical measurement application is to indicate the rotational speed of the shaft. One possible method to accomplish the measurement is for the shaft to be converted to an optical encoder, which generates certain number of electrical pulses for each rotation. To determine rotational speed, the pulse counter measures the number of pulses received during a certain time period and devices this by the time period and by the number of pulses in each revolution of encoders. A pulse generator is a device that produces a series of electrical pulses whose total number and frequency are specified by the computers. The total number of pulses might be used to drive the axis of a positioning system. The frequency of pulse trains or pulse rate could be used to control the rotational speed of a stepper motor. A pulse generator operates by repeatedly closing or opening an electrical contact, thus producing a sequence of discrete electrical pulses. The amplitude and frequency are designed to be compatible with the devices being controlled. Thank you.